All right, we'll pick up where we left off on 15.5. So again, the equilibrium constant K, since we don't use solids and liquids in calculating the equilibrium constant, we would just have LiOH, concentration of that squared, times H2 to the first power. All right, let's take a look at 15.6. All right, that says, what is the equation for the equilibrium constant for the following reaction? All right, I'm not going to write this one all out. You can just follow along in the book, but you can see that the first reactant is a solid, the second reactant is a solid, the first product is aqueous, the second product is aqueous, and the third product is a liquid. So the two solids in the liquid we would just throw out. So K is NH, the concentration of NH4OH, and that's squared because the coefficient is 2, times the concentration of BaSCN2, and that's to the first power. And so that's it. There's no denominator because the left side is just solids. All right. So that is 15.6. Now going back to your notes, we're at the bottom of page 2. It says the equilibrium constant K can be used to see if a reaction is at equilibrium, and if not, to see which direction the reaction will shift to achieve equilibrium. If the calculated K is less than the equilibrium K, the reaction must shift towards the products. So you're going to want to highlight that. And if the calculated K is greater than equilibrium K, the reaction must shift toward the reactants. Okay, so let's take a look at a on your own problem to show how you would deal with that kind of problem. So 15.7 is at the bottom of page 303, and we have 2 NH3 gas. That yields N2 gas plus 3 H2 gas. Now the problem says that the equilibrium constant is, so big K is equal to 17 molar squared. And then it says the chemist measures the concentrations of each substance to be for NH3 0.4 molars, N2 1.5 molars, and H2 1.3 molars. So is this reaction at equilibrium? So all we have to do is calculate K. And we'll see. If it equals 17, then it's at equilibrium. So the concentration of N2 is 1.5. The concentration of H2 is 1.3 molars. We've got to be careful. We have to cube that because the coefficient is 3. And then the concentration of NH3 is 0.4 molars. And we need to square that. Okay, so when you run that through your calculator, you'll get a K of 20.6. Now that is greater than the equilibrium constant of 17. Okay, so which way will the reaction shift? Okay, well, the calculated K is greater. Okay, so we need this number to get smaller, so we need our reactants to increase, okay, because they're in the denominator. In order for that number to get smaller, we need it to equal 17. So it must shift towards the reactants. So you could write that with a left arrow, okay? All right, so that is the math for this chapter. Okay, everything else is just concepts. So I will move on to Le Chatelier's principle. So in the book, we're on page 504. All right, and Le Chatelier was a French chemist who did a lot of work with equilibrium research. And his principle states that when a reaction at equilibrium is stressed. Now, when it's stressed, think of it, something changes. Okay, the reaction will shift to restore equilibrium. Okay, so let's look at page 504, figure 15.2. All right, you can see we have a reaction here, or the forward reaction, okay, and the reverse reaction. So products are making reactants, reactants are making products, and at 100 seconds they reach equilibrium. Okay, so they've hit equilibrium and they stay there till about 160 seconds. At that time the reaction is stressed. More H2 is added. Okay, we change something. So that shifts the equilibrium. The forward reaction, more collisions are occurring. Okay, the forward reaction moves up here and goes down, the reverse reaction goes here, and the equilibrium shifts to this higher reaction rate. Okay, so we stress the reaction by adding more H2. The equilibrium shifted upward to a higher rate. That's just what Le Chatelier's principle says. Okay, so there are three examples of stress that we will study in this class. Okay, changing concentration. All right, so that's what the graph just did. We added more H2, so that increased the concentration. Changing pressure, all right, and then changing temperature. Those are the three things that we're going to look at. Okay, now write this in your notes. Okay, next to this, write ignore solids and liquids as a source of stress. Okay, so solids and liquids, because they are 100% concentrated, they don't change, they don't stress a reaction. Okay, so first we're going to look at concentration. Concentration and Le Chatelier's principle. So changing concentrations affects the number of collisions. Okay, so let's go ahead, you can read over this, all right? So, but if product is continually removed, the reaction will always shift towards the products because the reverse reaction can't happen. If you don't have any products, you're not going to have a reverse reaction. But let's move on to 15.8, and I will show you how you can take a look at how concentration stresses and changes a chemical reaction. Okay, so 15.8, we have this reaction, CO2 gas plus H2 gas. Okay, we've got our double arrow. That makes CO gas plus H2O gas. Alright, and part A says what will happen to the concentration of CO and H2 if extra H2O is added to the system. Okay, the way I like to do this says what will happen to CO, so I'm going to put a question mark right there underneath CO, and H2, so let's put another question mark under H2. If extra H2O is added to the system, so I'm going to write a plus and an arrow. We've added more H2O. Okay, so this is how you can analyze and see what's going to happen. If we add H2O to the right side, more collisions will occur on the right side. That means the right side is going to win. If the right side wins, the arrow is pushed this way to the left. Okay? Right side wins. So think of the arrow as a hose. Okay? So it's shooting products from this side over to this side. Okay, so what will happen? Well, if you're on this end of the arrow, just like if you were on this end of the hose, you're going to get more. So H2 will increase. If you're on this end of the hose, the back end of the hose, you're going to lose. Okay, you're going to lose the quantity. Okay, so CO will decrease. All right, so let's try another one. So part B says what will happen to the concentration of CO2, so I'm going to put a question mark there, and H2O, so let's put a question mark over here at H2O, if CO is removed. Okay, so I'm going to put a down arrow and a minus sign. CO is removed. Well, if CO is removed, fewer collisions occur on the right side. So the left side will win. And if the left side wins, the arrow shoots this way. Okay, so what's going to happen to CO2 if the arrow is shooting to the right? Well, it's on the back end of the arrow. Okay, so it will decrease. What will happen to H2O? Well, it's on the kind of the hose end of the arrow. It will gain, so it will increase. Okay, let's try one more. So C says what will happen to the concentration of CO, so put a question mark there. And H2, we'll put a question mark there. If extra CO2 is added, so we're adding CO2, so plus, and the arrow is up. If we add CO2, CO2 is on the left, more collisions on the left side will win. Okay, so on B, the right side, the left side won. Okay, so again, the left side will win. That'll shoot our arrow to the right. Okay, so what will happen to H2? It will decrease. And what will happen to CO? It will increase. So if you can get the arrow pointed in the right direction, it's really easy. Just think about which side wins, the arrow will shoot the other direction, and then things that are on the business end, the arrowhead end, are going to increase. And then things that are on the back of the end of the arrow will decrease. So that is Le Chatelier's principle for concentrations. Now temperature and pressure are much easier to analyze. Okay, so let's go back to your notes. We're on page 4. Pressure and Le Chatelier's principle. Increasing pressure increases collisions for gases. So we are only concerned about gases when we're looking at pressure. Okay? Don't care about aqueous, solids, or liquids. So changes in pressure are a source of stress only for gases. When pressure is increased, equilibrium shifts away from the side of the reaction with the most gas molecules. So we're just going to add up the coefficients of the gas molecules. All right, the side that has the most, okay, if the pressure is increased, it shifts the reaction the other direction. Okay, so you're going to want to highlight that. Highlight when pressure is decreased, equilibrium shifts towards the side with the most gas molecules. Changes in pressure have no effect if gas molecules on each side are the same. All right, so let's take a look at 15.9. Okay, 15.9, we have 2 SO2 gas plus O2 gas, and that makes 2 SO3 gas. So everything is gas. So what I'm going to do is add up the gas molecules on the left side. Okay, on the left side, you just look at the coefficients. 2 plus 1. On the left side, we have 3. On the right side, we just have 2 gas moles. Okay, moles, molecules, it's they're both, in this case, you can think of them as the same. Okay, so part A says, which way will the reaction shift if the pressure is increased? So if pressure is increased, the reaction shifts away from the side with the most gas molecules. Okay, well, the left side has the most, so it's going to shift the other way. Okay. So we would increase SO3 and decrease SO2 and O2. Part B says, which way will the reaction shift if the pressure is decreased? Well, just the other direction, okay, to the left. All right, so the right side would decrease, and the left side would increase. Okay, and the last part of Le Chatelier's principle is temperature and Le Chatelier's principle. Okay, so when temperature is raised, the reaction shifts away from the side with energy. So, very simple, when the temperature is lowered, the reaction shifts towards the side with energy. Positive energy is a reactant, it means it's endothermic, so going back to chapter 13. Negative energy is a product, meaning it's exothermic. Okay, so let's take a look at 15.10. We are on page 513. All right, 15.10, we're going to consider the following reaction. CaCO3, that's a solid.